Good morning, everyone. My name is Carlos Moreno, and I'm here today representing a collaborative research effort from the Central University of Venezuela and San Longoyo Institute of Engineering and Technology in India and Jacksonville State University in the US. We are delighted to present our work at Modern Systems 2025 conference within the Meta IoT special track. Our presentation is titled Development of WebRTC-Based Video Calling Application to Predict Quality of Service Patterns using an Artificial Neural Network. My most relevant background is that I received my PhD in telecommunications and computer science from Telecom Sud Paris, jointly with the University of Paris 6 Pierre et Marie Curie in 2009. I completed postdoctoral research fellowship funded by the Carland Foundation of Spain at the Polytechnic University of Madrid in Spain in 2022. I earned a master's degree in Big Data and Business Intelligence from Next Educación in collaboration with University Isabel I in Spain 2024. I also earned an MBA and I'm a specialist in, and I have a master's degree also in data networks from Central University of Venezuela, and I'm an electronics engineer. Currently, I'm professor at Central University of Venezuela. I teach in collaboration with Universidad Internacional de La Rioja in Spain, OBS Business School in Barcelona, Spain, and Next Educación in Madrid. This is my team, which is conformed by myself, engineer Ezequiel Frias, who is an expert in Python, Java, script developer, AI architectures, quality of service in IP networks. My colleague and friend Vinod Kumar is an expert in big data, Internet of Things, artificial intelligence, sensor networks, trustworthiness, and cybersecurity. And my other colleague and friend is Eric Games, which is a specialist in IP networks, IPv6, cybersecurity, VANET, SDN, and SCADA systems. Here's the outline for today's talk. We will begin by discussing the motivation behind integrating artificial intelligence into real-time communications, followed by a review of the state of the art. We will then formalize our problem statement and questions. The core of the presentation will cover our methodology, focusing on scenario establishment, neural network development, and prediction testing. Finally, we will analyze the results across 4 distinct network environments and present our conclusions and future work. Real-time communications has evolved significantly over the past few decades. We moved from early peer-to-peer technologies through structured protocols like SIP to the emergence of the Web Real-Time Communication, or WebRTC. It's an efficient open-source technology that enables real-time peer-to-peer audio, video, and data transmission directly between browsers, eliminating the need for plugins or external software. The standardization of WebRTC APIs by 2021 underscored its permanence and versatility. Simultaneously, the application of artificial intelligence in video communications has rapidly advanced, moving from basic supervised machine learning techniques like linear regression, SVM, decision trees, to deep learning architectures, notably convolutional and recurrent neural networks, CNNs, and LSTMs. This transition addresses critical quality of service indicators such as jitter, latency, and packet loss, as well as quality of experience, metrics like MOS, PSNR, SSIM. A lot of research is going on with this kind of things. Regarding the state of the art, the study of quality of service prediction using an AI is well established. Prior work has used various machine learning models, including isolation forest and XGBoost for anomaly detection in network traffic. Other research successfully applied artificial neural networks for failure prediction in IP networks. We also have proposals of architectures like TAQ, GRNN. However, many of these foundational works, while impactful, don't specifically consider WebRTC as the base technology. Some other works in non-WebRTC have studied content-aware network traffic predictions dynamically, online multimedia traffic classification, and deep learning models for service quality of service predictions based on feature mapping and inference. Research utilizing machine learning within WebRTC is growing each time. For instance, industry leaders like Google have deployed machine learning-based bandwidth estimation systems that leverage a combination of LSTM and test layer architecture. These works confirm that the WebRTC client statistics provided via API are viable source for deep learning models. Sorry, there's a lot of noise. Research questions. Problem formulation. Given the critical role of quality of service in ensuring an optimal user experience in video calls, our research was designed to address two primary questions. First, which quality of service metrics can be considered to measure, analyze, and predict quality of service patterns? Second, which specific type of neural network predicts quality of service better in a WebRTC-based video call? For this, we have the context. This context is our collaboration project between Universidad Central de Venezuela, SLIET from India, and JSU from the United States of America. Regarding the methodology, our methodology began by identifying three critical quality of service parameters in WebRTC: latency, jitter, and packet loss rate. The client with a network conditioner tool at left side is connected to the internet via the simple fiber provider using 400 megabits per second fiber optic. We also have a Wi-Fi 5 at left side, the band of 5 gigahertz with channels of 80 megahertz width. At right side, we have another provider. The name is Net1 provider with the same characteristic, except that we have a lower bandwidth of optical fiber. This network link conditioner is a software to create the scenarios that we're going to explain on the next slides. We configure WebRTC clients on each side by using React, JavaScript, and Pure.js. And we also configure a WebRTC server by using Node.js and Socket.io. Based on the ITUT G1010 recommendation, we established 4 representative scenarios to validate the solution. We have scenario 1, acceptable quality, moderate degradation, number 2, number 3, critical quality, and number 4, extreme conditions. As we can see on this table, from top to down, we decrease the bandwidth available. With the latency, we can see that we increase the latency. And regarding packet loss rate, we can see that it's increased. These scenarios are created by using this tool, Network Link Conditioner, scenarios produced by Apple laptop. So we have to talk about the development of the neural network. For the analysis of patterns and the prediction of network conditions based on the collected metrics, it was decided to implement an RNN 4x4 layers, one input layer receiving the 6 quality of service metric values, one RNN layer, hidden one, and one test layer, the second hidden layer, and output reshape that redimension the test layer, outputting the 6 predicted quality of service metric values. As we can see, we have latency, jitter, and packet loss for video, latency, jitter, and packet loss for audio. This is the entrance of the neural network, and we have the prediction. We implemented, as we said before, a recurrent neural network architecture, which is inherently designed to handle situation time series data like quality of service metrics. We had 4 possibilities. We can see on the table the hyperparameters. Finally, we decided to use the LSTM M. The models were trained on a general data set encompassing all 4 scenarios during 1 hour approximately with 80% and were applied to 20%, one call of 5 minutes per scenario. We chose the best one. Initially, we considered the MAA, mean absolute error, but finally, we realized that all the indicators are important just to choose which is the best LSTM. Multiple outputs, it means that we have many steps. Based on the data obtained from each sample, structured JSON objects were built and loaded to a Firebase Firestore database, non-SQL, as we can see. A Python code created fills out a pandas data frame with the data loaded and executes pre-processing and transformation. Round trip is divided by 2 to get the latency. For instance, packet loss rate is calculated from packet loss and packet received for video and audio separately. We use the paradigm ELT, which stands for extraction, loading, and transformation. So we decided to have this architecture with LSTM cell and an historical data of 60 steps. And we have a prediction of 30 steps ahead of the 6 values for each indicator. I mean, this is going to be a solution, and it's going to be within the JavaScript WebRTC implementation, which is our contribution in the practical work. Now we can talk about the results. In the case of scenario 1, acceptable quality. In the case of the video, the model successfully estimated the video latency closely following the actual signal trend. No significant offset or error accumulation were observed, demonstrating the model's ability to adapt to stable network conditions. Although the model accurately predicted most video jitter values, an outlier near 500 milliseconds, indicating an anomaly in an otherwise stable network. It can be noted that in the video packet loss rate was practically 0 throughout the whole experiment, with the model predicting values close to 0. If we go to the audio graphics, the audio latency predictions exhibited a high level of agreement with the actual data. The model was able to maintain the trend without notable deviations, validating its ability to model this metric properly in low variability environments. The audio jitter was predicted with minimal errors, showing highly stable behavior. This reinforces the idea that under ideal conditions, the model was capable of accurately capturing slight fluctuations in audio quality. The audio packet loss rate prediction remained near 0, close to the measured data. We can pass to the scenario 2 regarding video. It can be seen that the video latency showed an increase in variability compared to the acceptable quality network scenario. While the model adapted well to average values, it exhibited limitations in predicting suddenly latency spikes, as we can see, which expected given the less stable nature of the network in this scenario. The video jitter showed greater dispersion than the first scenario. Nevertheless, the model could follow the overall trend, though with slightly reduced accuracy. Regarding the video packet loss, figure indicates that the model faced greatly difficulties in anticipating the actual pattern due to the intermittent and unpredictable nature of this type of traffic on the congested network. Even so, it managed to represent the overall trend of the fluctuations currently. Let's pass to the scenario 3. Regarding the scenario 3, figure shows a pronounced deviation between the actual video latency values and model's prediction. Although the model was generally able to follow the trend, differences in absolute values were evident, especially during periods of higher delay. This lack of precision can be attributed to the high baseline latency and the significant network instability. It can be seen that in the case of video jitter, the model showed relatively stable performance. However, it struggled to replicate certain abrupt peaks present in the actual data. Despite this, the predictions reasonably captured the overall jitter dynamics, demonstrating the model's partial ability to adapt to rapid delay variations under critical conditions. Regarding the video packet loss rate, with this scenario number 3, figure indicates that the predictions generally remained close to the actual values. However, fluctuations were observed that the model was unable to predict accurately. Regarding the audio, for the scenario 3, similar to the video latency, the audio latency also suffered discrepancies as shown in figure. Although the model reasonably followed the trend, significance were noted at the highest delay peaks. As depicted, the audio jitter also exhibited behavior similar to that of video. The model managed to follow the overall trend, but faced notable difficulties during sudden changes. This illustrates that while the model can adapt to moderate fluctuations, it has limitations when faced with unstable events. As shown in figure, the audio packet loss rate exhibited patterns similar to those of video. That is, while the model's predictions generally track the actual values, discrepancy emerged, reflecting its difficulty in anticipating abrupt changes. We now arrive to the scenario number 4. Regarding the video, as we can see in figure, the model was able to reasonably follow the behavior of the video latency, adequately reproducing the most significant peaks present in the actual data. It can be seen that in the case of the video jitter, the model showed a reasonable ability to follow the general signal dynamics, although with specific differences in the maximum values. The predictions were consistent with the variation patterns, reflecting the model and ability to capture the changes. We have only 10 minutes left. We have to finish soon. Regarding video packet loss rate, indicates an average of 2 percentage points. Regarding the audio, in contrast with the video latency, the audio latency predictions exhibited greater deviation from the actual values. As with the video jitter, reveals that the audio jitter predictions provided an acceptable representation of the signal variation. There are some discrepancies, but the model is working. So regarding the packet loss rate, the figure showed that the audio packet loss rate prediction reproduced the general structure of the actual data. We arrived to the conclusions at this time. To conclude, our research successfully demonstrated that integrated WebRTC technology and recurrent neural networks constitutes a viable modern alternative for quality of service prediction in video call applications. WebRTC simplified the development of real-time communications environments with robust measurement capabilities. We found that LSTM-type neural networks are capable of capturing the temporal behavior of the key quality of service metrics, latency, jitter, and packet loss rate. The model achieved acceptable accuracy, particularly under stable or moderated degraded conditions. One of the most significant contributions of this work is providing that the deep learning model can generate reliable predictions of future behavior simply by analyzing the few first minutes of a call. Furthermore, training the model across multiple network scenarios enhances its robustness, allowing it to generalize better under diverse and fluctuating real-world conditions. Regarding the future work, we can say that based on our findings, we propose several avenues for future research. We recommend expansion of the data set, inclusion of new quality of service and quality of experience metrics, implementation of a model in real production environments, exploration of more complex architectures, and finally, designing of autonomous network management systems. I thank you all for your attention. As Albert Einstein once said, the important thing is not to stop questioning. I'm now open to your questions and comments. Please feel free to reach out via email or WhatsApp if you have any follow-up for your inquiries. Thank you very much. If you have any questions, my friend Vino is speaking. Cosmin, do you have any question at this time?
Yes, hi. I see Vinod is trying to speak, but his microphone is off.
Yes.
Now it is fine.
Yes,
I'm
listening to you.
So,
fine.
Yeah. Professor Carlos, it was an excellent position, and you said as a chair of this IoT special session, I would like to say that this is really a technical presentation.
Get closer, please. Closer. Yes.
Yeah.
Yeah.
Am I audible?
It's better.
Yeah. Am I audible now?
Yes. We can hear you.
Yeah.
Better, yes.
Yeah. It was an excellent presentation. As a chair of this Meta IoT special session, I congratulate you for this presentation. So I would like to ask the audience if any questions, any queries. We are open to the questions and concerns. Please ask and be quick because we have few minutes left.
Yes.
Hi. I do have a question because this is related to real-time communication, and while we can measure network aspects and jitter and latency and all of that stuff, the real-time aspect is very much a human assessment.
Yes.
And my question is, are there any standards with respect to, let's say, the technical measurable parts that are sort of calibrated to to decide, is this real time or is it not real time?
Okay. That's a very good question because according to the International Telecommunications Unit, the ITUT, we have some recommendations. For example, the maximum delay should be less than 150 milliseconds in one direction in the case of interactivity, and there are some limits, recommendation of limits for jitter and for packet loss rate, but it's an extremely large document which I can give you if you need it. The recommendation G1010 establishes some of the standards for that. And there are some other documents from ITUT which go deeper into the details. They don't explain how to measure it. They just show the limits. But in the real world, some enterprises, they also have white papers and they recommend their own values. For example, Cisco systems, they have their own values because they have a lot of experience. ITU comes from the traditional circuit systems, and Cisco is from the packet network world, and nowadays we're including both worlds, and these organizations bodies try to establish limits, but both enterprises, organisms are working together. There's no way to standardize how to measure it. You can use Wireshark, the analyzer. You can use open source like iPerf. You can use a lot of tools, but what is common always is that every time you measure, you have an impact of the measurement. Anyway, you know, one of the questions of my member of my jury in my PhD, she asked to me why there were some peaks on the establishing time, for example, and she asked if there was a timing error. And I responded at that time, in 2009, in France, by the way, that it was not a timing problem because there was an RFC of the SIP protocol, which explained why there were some peaks. Do I explain myself? So,
Yeah.
so there's no way of establish how to measure it.
Okay.
If you have any other question, inquiries, you can send to me an email and I can answer, because I have a line of research of how to use, how influences the cybersecurity of the quality of service. We have published some papers with Dr. Vinod Verma in 2009 in Stockholm. So in Sweden, we have another paper that we can show to you.
I see.
Right?
Okay. That answers my question. Thank you. Thank you.
You're welcome.
Yeah. Yeah. Any other question from audience? Anybody else? Because lagging the times, like I think we have 1 or 2 minutes left for the meeting. Anybody else? Any audience, please? No, I don't think so. We have any more questions. So thank you so much once again, Professor Carlos, for your wonderful presentation. And as the chair of this meta-IoT session, I also thanks to all the audience presence here in this online virtual room. Like, thank you so much, all of you. Please be in touch and stay safe, all of you. Thank you so much. Bye-bye and take care.
Thank you very much. Bye.
Thank you all.